Hi everyone and welcome to Aviatrix Deep Dive with Saad. In this session I'll be discussing about the hybrid connectivity for Azure. Like any other cloud, there are two main ways you can connect your on-prem environment. When I'm talking about the on-prem, it means your data center, your branches, your partners connectivity to Azure cloud. It could be using the private circuit like Express Route, or it could be using the internet, which is the public circuit. Even in the private and the public circuits, there are many different ways you can connect, like unencrypted, encrypted, standard encryption, and high-performance encryption. We'll be discussing all those in this session. With that, let's discuss the first one without any kind of end-to-end encryption, right? Using the private circuits. So this one is using private circuits without end-to-end encryption. You will still see some encryption over there when you see Aviatrix Architecture. So let's draw it out first. We have Aviatrix multi-cloud network architecture, spoke and transit architecture. On top you see Aviatrix spoke VNets. Let's say this is spoke VNet, and this is another spoke VNet. In spoke VNet, we have spoke gateways. This is a transit VNet. In transit VNet, we have transit gateways. And spoke and transit are connected to each other. These are 4 connections from each VNet because of the active mesh. For the ease of understanding and drawing, I'm just drawing only single connection right now. And then we need to have, since we are talking about without any kind of encryption, then we are going to utilize one more VNet here. And by the way, this VNet, you can call it as a BGP or LAN VNet. So I'm going to say BGP or LAN VNet. And I'm going to describe like why I'm calling it BGP or LAN VNet. So first, let's see what we have from on-prem. So on-prem, we have a WAN router. And then the WAN router is going to have the connectivity using the express route circuits. I'm going to just draw one circuit right now. And then in BGP over LAN VNet, we are going to attach the express route with the ER gateway, express route gateway. We are going to utilize the Azure route server over here as well. So I'm going to just write ARS, since ARS are always going to be deployed in high availability. So ARS1 and ARS2, two ARSs over here. And in order for the ER gateway and ARS to exchange our routes, we need to make sure enable the B2B knob over there. Okay, now we wanted to make sure the routes which we are advertising from on-prem over to the Azure environment, they get all the way to the spoke VNets. So how we are going to connect these transit gateways to the ARS? So in order for us to do something like that, first we need to have the VNet peering between these two VNets. And this VNet peering you can create using the Aviatrix controller also. So I'm going to just call it a VNet peering. Okay. And then what are we going to do over here? We are going to create a mesh of BGP over LAN connectivity. So this connectivity, this is not IPsec. We are not using any of the tunneling protocols over here. This is pure vanilla BGP connectivity and without any kind of a throughput limitations. So whatever natively the throughput is provided by the VNet peering that you are going to get. All right, so we create a mesh between the transit gateways and the ARS so they can exchange the routes now. So this is called the active mesh peering. The connectivity between the transit gateways and the ARS again is going to be on the private IPs. Now, if I'm going to show you a couple of routes over here, let's say this on-prem is advertising 192 route and also a non-RFC 19 route. Let's say this is 9.9.0.0 route. Okay, these routes are being advertised. There is a BGP running between the on-prem and the ER gateway. So using the BGP, ER gateway receives a route. And because of our B2B knob that we activated, ARS is going to receive those routes in the fabric. Now ARS has a BGP adjacency. So this is BGP adjacency with the Aviatrix transit gateway. Now transit gateways are going to receive all these routes, like 192 route, which is RFC 1918, and non-RFC 1918 route, which is the 9 route to the transit gateway. Now Aviatrix controller is going to do its magic, and it's going to propagate these routes. It's going to take these routes and then propagate into all the spoke gateways. This is called the software-defined routing, or SDA routing in short. Since you are advertising the non-RFC 1918 route also from on-prem, the applications over here in these spoke VNets also need to access this environment, which is a non-RFC environment in on-prem world. So what controller is going to do, controller is going to create these non-RFC 1918 routes in the VNet routing tables also. So that's all done by Aviatrix controller. From the top down, on-prem also needs to have access to these spoke VNets address spaces as well. Once you attach the spoke gateways to the transit gateways knows about all the spoke VNets address spaces, and then the address spaces from the transit gateway is being advertised using the BGP over to the ARS. ARS is going to forward, or ER gateway is actually going to receive that, and then ER gateway is going to advertise it back to the on-prem. So that's how you are going to get end-to-end connectivity or end-to-end route propagation. All right, so let's talk about the second option, which is again still going to be on the private circuit, but now we are going to discuss about the end-to-end encryption. But prior to that, let's take a look at it. Why I'm calling it the without end-to-end encryption is because up till here we don't have any encryption, right? Up till here, no encryption. From here, we have either a standard encryption or a high-performance encryption, depending on what feature and functionality you used while you were building the Aviatrix Transit architecture with transit and spoke gateways. So now let's talk about the standard encryption using, again, the private circuits. The architecture is going to be remains the same. All right, so let's take a look at this architecture, which I have just drawn on the right-hand side. Here, this is the standard encryption. Aviatrix Transit architecture over here on top. And then from on-prem, we do have the express route. Same thing over here. The express route is here too. And then we are exchanging the routes from the on-prem and then the VNG using the BGP. So the VNG has those routes, and then Aviatrix Transit now are going to receive this route using its ETH2 interface, and then from there it can get to the fabric, and then from there it can get all the way down. So what do I mean by that? In this scenario, this is specific to Azure, where when you attach the VNG and then you create the BGP adjacency, then the routing table of this transit VNet is going to have all the routes from the on-prem too, right? In this scenario, since transit gateway does not has a way to get to on-prem router over here, which is the WAN router, what it's going to do, it's going to rely on its quad 0 route, and then which points towards its ETH interface of this VNet, where the routing table has all the routes learned through the VNG. So that's how it can know about the WAN router interface. So when you are building this BGP, basically you are going to advertise the connector interface to the VNG, and VNG is going to advertise the entire address space of the transit VNet. So now it becomes easier for the Aviatrix transit gateways to build the IPsec connectivity, the overlay with the on-prem router like this, because the transit gateways knows how to reach the interface on the WAN router, and same thing with the WAN router, because the VNG already advertised the transit address space. So it becomes much easier. So now you build your IPsec overlay, and the routes are going to be advertised using the BGP. So hundreds and thousands of routes, whatever you want to advertise, you can advertise it out like this. So same thing is going to happen, similar to what I just described using the private circuits. Routes going to get to the Aviatrix transit, and then the Aviatrix controller is going to pull the routes and program into the spoke, and if it's non-RFC 1918 route, then it's going to be programmed into the VNet, spoke VNet routing tables for end-to-end connectivity. All right, so let's talk about the high-performance encryption using the private circuit. I'm going to reuse the same architecture, and instead of terminating the overlay on the WAN router, what you are going to do at this point, you are going to deploy the Aviatrix, let me do this over here, Aviatrix Secure Edge, which is the software appliance in your data center or colo. So this is Aviatrix Edge, and then instead of building the overlay with the WAN router, you are going to build it with this. So the number of tunnels depends on the size of the transit gateways in the Azure Transit VNet, and you really don't need to build these connections. Everything will be built by the same Aviatrix controller, and these are all self-managed tunnels, and you can get 10 gig plus connectivity over here. These Aviatrix Secure Edge devices, if you have a multi-cloud environment, then you can use the same devices to connect to your AWS, GCP, or OCI world too. So you can build your tunnels similar way. If there is another transit on this side, then you can connect to that. So now let's talk about the public circuit, which is internet in our scenario. Aviatrix MCNA, the transit architecture is going to remain the same. We have spoke gateways, and we have transit gateways in transit VNet. We connect them together. It is going to be standard end-to-end encryption in this scenario. So this is all encrypted, and then from here we do have internet as a medium. We are going to utilize the public IPs on the transit gateways and the public IPs on your on-prem router, WAN router as well. So what are you going to do at that point? You are going to build the IPsec connectivity to on-prem router. Typically, these are two routers for redundancy, but for the sake of the simplicity, I'm just drawing one, and then you build your IPsec tunnel. Your routes from on-prem will be advertised out using the BGP connectivity and IPsec like this. route gets to the transit gateway, the controller picks them up and then propagates the routes to the spoke gateway, and also if these are non-RFC 1918 routes, then it will create those routes in the VNet routing table as well. The other option that you can have is the high performance encryption. So HPE, and this time it's again end-to-end encryption also. So the difference over here is going to be, instead of terminating the routes like the previously which we discussed, we are going to deploy the Aviatrix secure edge devices, either on-prem or colo, and then terminate the IPsec tunnels directly onto Aviatrix edge devices. These edge devices are managed by the Aviatrix controller, and so you really don't need to create these IPsec tunnels manually over there. Again, similar to that architecture, the number of tunnel depends on the size of the transit gateways, and then the performance depends here because we are relying on the internet, the size of the internet pipe which you have bought, right? Okay, and by the way, again, like the other private circuits, these tunnels are self-managed tunnels, right? Again, through the Aviatrix controller. So this is what I have for Azure hybrid cloud connectivity. In the next session, we will be talking about the active mesh.